All right, so well, you probably should fix your audio then. But what are you gonna do? Oh yeah, hydrolysis of like acetals or whatever. I guess amines and the other ones too. It all works for all of them really. But kind of I just want to do one example of like the reverse mechanism for hydrolysis. I think we do last week. So let's see, there's a problem we did. I just wanted to, oh yeah, there we go. So yeah, we'll just do the first one here, 9.23a, but we'll just show the mechanism for this, right? So these were the products, right? But in case you're kind of asked a mechanism where you're given one of those groups, right? It's literally just kind of the reverse steps of what we did when we formed them, right? Anhydrins, yeah, amines, yeah, enamines, acetals, and yeah, I believe that should be the all reversible ones. The other ones go to completion, like Grignards. Sulfur ones too are technically reversible. Grignards, yeah, all the carbon nucleophiles are basically the ones that go completely forward, and I guess hydrogen nucleophiles too. In that case, like LAH. But I'm not going to really do LAH or Grignard. You guys have already seen those multiple times between Orgo 1 and probably earlier in the semester too. So that's why I'm only doing the Wittig here, because that's new, right? Grignards and LAH should be a very simple mechanism. Okay, so let's do, what was it, 9.23? Let's change the color. All right, so we had this. And I kind of want to pick another one just because the structure is annoying to draw. Yeah, the Grignards are not reversible, right? Because when your Grignard attacks, it's going to form the carbon-carbon bond. Can't really destroy that bond, right? The whole point of the other bonds is that when you have heteroatoms involved, they can get protonated, right? So under acidic conditions, right, you could essentially just reverse the reaction. Grignards and Wittig, and I think it is, well, you guys didn't learn Bayer-Villager oxidation, but those are not reversible processes. Okay, so we did this. We did last week where we got the products. I'll just draw the product here, which is this plus the diol here. So in terms of its mechanism, right, it's pretty straightforward. You can really just start with really one of these OR groups, right, and just start with protonating them, right? So it's 2H plus. It's going to get protonated. So, yes. Okay, right. Now it's literally reverse. So remember, last step was deprotonation. Then before that was the carbonyl, right? So now it's you're reforming your carbonyl here. Literally, it's just the backwards orders, right? And then you're clicking this part off. In this case, it'll still be attached, right? Next up, where is it? Guess we could go this direction. And we have this and 1, 2. The carbons are in between 2, 3. There you go. Right. And you have a double bond here. This should be +7, right? Now here, right, in this case, you have water present, right? And remember, we're trying to form the original carbonyl, right? Or, I guess you could call them nucleophilic additions, but your carbonyl was lost, right? The original carbonyl, technically, right, it left as water, right? So water has to come back in to form that, right? I'll go back up later, Jared. So now we could just take, let's go down this way. Let's grab some water. And it attacks there, right? Opens this up. Now you have, oh man, this is going to draw. 1, 2, 3, oh. Yeah, the water is the nucleophile in this case, right? If we go look at your notes from the original formation of acetals or amines or all of that, right? At a certain point, water leaves, right? That's the original carbonyl, like leaving basically, right? That's why you could consider this kind of like nucleophilic substitution, but your carbonyl is lost, right? It's kind of a good way to kind of look at it. Okay, so now we just have a proton transfer. Water gets deprotonated, or you could just do internal transfer and protonate that originally. Doesn't really matter which way you do it. It's going to show both steps. One, two, three, H. And now this is just OH. That OR gets protonated. And now we reform our actual carbonyl. There's a link tree I put in the WhatsApp now that has every link you need for the class. And then we have our kind of floating alcohol here. It's diol, I should say. Right. And then your last step is just another deprotonation. Get your product.
Do
Cyclopentanone.
you mind if I ask a question? Just a quick question.
Yeah.
The wiggly H, are you allowed to use it for like one-step protonation, deprotonation? Because usually I've seen Bisco use it only for the intramolecular to skip 2 steps basically when you're protonating something and deprotonating something at the same time.
Like I said, that's something you will have to ask him. I guess you guys are doing on Tuesday, the exam review or whatever. Ask him that. I'm just doing this for shorthand in terms of the mechanisms, right?
Okay.
I think the first time I did it, I showed all the actual protonation arrows. It really comes down to it's really what he'll accept, right? Because a proton transfer is just simple, right? It's just literally whatever your thing is acting as a base, it grabs a proton, and if it's bonded to something, that returns, right? So that's why I don't really draw those out, because it's kind of just a waste of time in terms of what it is. Everyone hopefully should, at this point, be comfortable with proton transfers.
Got it.
Yep. So yeah, just confirm confirm with him, and also those who are in Boson's class, is confirm with him how they like, if they want you to show the full arrows or what for the proton transfers. I'm just shorthanding it right now so that we could, get to other stuff. Okay, so yeah, that's hydrolysis really, right? It's literally just the reverse, right? I just want to do one example, so like that way, if you do see it, right, you wouldn't be like surprised, like, oh, what's happening, right? Like I said, you always have to make sure you identify those bonds, right? Like in this case, it's an acetal, it'll be OCO, right? So acetal is always OCO, like that, right? And then this carbon here, whatever it's connected to, whatever those R's are, right? That was the original carbonyl. You have a enamine, sorry, imine, same thing, R, original carbonyl, those R's. What other ones do we have here? We have enamines. Is this, call this R for now. R. It looks like this. And I guess anhydrins are easy to recognize and all that, but like those ones are a little harder for people to recognize. But whenever you see that functional group, right, and you're just introducing acid to it, like let's say you get it on question 3 or 4 as one of those reaction questions, just be able to immediately identify, okay, that's just gonna turn back into a carbonyl, right? Literally just the reverse. Okay, so really the only thing left from chapter 19 that I just want to do a little bit of practice on was the Wittig reaction, right?
Sure.
Yes.
Could you go back to the screen for a second? Okay, thank you.
Okay, let me find some Wittig stuff here.
I'm sorry, what were you saying about those 6 carbonyls?
What, these?
Yeah.
Basically, if you go, if you see those top 3 functional groups, right, and you just introduce them to acid, like hydrolysis conditions, right, they're going to return to carbonyls. So that's why being able to identify those in a structure is important, right? You good there? Okay. All right, so the Wittig reaction is a pretty cool reaction. Actually do an example of creating the Wittig reagent in case you're given like the full thing. So it's a good example here. Yes. I guess we can just create an alkyl Wittig reagent. Okay, so we'll just do like, yes, ethyl Wittig, right? So this is Wittig, right? In terms of reagent prep, right? Let's say you had something like ethyl bromide, right? Really what you're looking for is you're given these conditions, right? That's ethyl, okay, just want to make sure I'm doing it right. PPH3, so that's triphenylphosphine. And the second is, I guess it doesn't matter which butyllithium you use. Usually when it's butyllithium like that, it refers to N-butyllithium, which is like the linear change, but you could probably use sec-butyllithium too. The main purpose is just a very strong base, right? And I guess technically the, what is it? Lithium does coordinate with the counter ion, but it's not really too important. Okay, so then the first step is pretty simple, right? Put this. Hopefully you don't get a reaction like a, what is it? A reagent prep for it. Usually you'll just give you the actual reagent and then like ask you to do just to get the product for it. So this, after step 1, you get PH3, right? And now really just the second step is literally just the base coming in, butyl lithium. So this is always annoying to draw. 1, 2, 3, 4. Basically anionic this thing, but I'll just show it from the bond. It doesn't really matter which way you draw it. And then we could just grab a proton here. Okay, then you have your reagent. Right, so as it is right now, oh, I am missing something, right? Yeah, there you go. Thank you. Like, why did I not get the yellow? That's why, because I forgot my positive charge there, right? PPH3 was neutral when it did the attack. So if it gave up its electron pair, it gained a formal charge, right? So there you have what's called a yelid, right? Or I guess this is your phosphorus yelid, right? Yelid is really any Zwitter ion. So it's kind of old terminology from Gen Chem, but any Zwitter ion is something that has like multiple formal charges. Yelids specifically are when they are right next to each other, one atom away, right? And this kind of has two forms, right? It has the yelid form, and then the other form, which is, anyone know what's the name of this kind of form, where it's double bonded? I don't know if your professors might have mentioned it or not. But if no one knows, it's called phosphoryne. Right, so there's the yelid form where you show both negative and positive charges, right? And then when you have it double bonded, right, that's called the phosphoryne form. It doesn't really matter which form. It is easier to do the reaction with the yelid, though. I will say that in terms of actually drawing out the reaction. So I guess we could do an example of this one, right? What is this? We created the ethyl Wittig. So let's say we had this. Let's draw out a carbonyl. Actually, let me see if they have any examples down here. Oh, they don't. Okay, we'll just do a simple example then. Guess I'll just pick acetone. Actually, I'm gonna put formaldehyde for a specific reason. Okay, so the reaction kind of goes, it's kind of like similar in terms of like I guess like a cycloaddition, technically, right? Basically what you have is, you know what? Let's make this pH. Why not? Just to kind of highlight the main point here.
Sharuk,
Yeah,
are you done with the Wittig reaction?
we're doing it right now.
Okay, can you like zoom out a little bit?
After I do this, I'm
Okay.
in the middle of this right now. Okay, anyways, so right, you have your always draw the yelid form. I don't know if you'll be asked on the mechanism directly. Just want to discuss it once again. I mean, you guys probably did it in class, but it's kind of always good to do. So basically what it is actually, let me draw this a little slightly differently. Kind of have it lined up like this, be better. Minus, plus, right? So your carbonyl, right, is going to attack the electron poor phosphorus, right? Your carbanion next to your phosphorus, right, is going to bond the electronegative, or it's not electronegative, electron poor carbon of the carbonyl, right? So it's literally a 2+2 addition, right? You have two electrons coming from the carbonyl bond, and then 2 electrons coming from the carbanion. Right? And technically, you could draw it the other way too, but doesn't make too much of a difference, right? Okay, so then you kind of get this intermediate that looks like this. So in this case, what's this? Actually, I draw this a little better here. Let's draw the oxygen bond first. Then we have bonded over here, the ethyl. Here, it's gonna be carbon, carbon, right? And then one of these is just pH technically. And there is also the H that's off there, but
Why did
you know
you
what?
turn it over?
What do you mean turn it over?
Like the oxygen was on the left side and the pH3 was on the right side.
I mean, it doesn't really make a difference, but I guess it in terms
Yeah,
of
like
clarity.
I just like consistency because I get confused. Thank you.
Yep. Right, so you have this kind of cyclic intermediate, right? And then really what happens next is you form a olefin or alkene, right? Between the carbon here. So let's just mark some carbons here just in case people are still confused, right? This is this carbon, right? And let's use blue for the other one, right? Is this carbon here, right? So essentially what we're doing is, let's make this arrow red too, right? This is the carbon-carbon bond we are forming, right? And then what happens here is basically the phosphorus carbon bond will break and a phosphorus oxygen bond will form, right? Here. So here is coming in like this. This is coming in like that, right? And that's how you form that alkene olefin, right? And then now if you draw the Newman projections, you'll see exactly why it's going to be Z, right? But they don't really go into that detail or undergraduate level for that. But the main outcome is that when it's unstabilized, is that sorry, I keep saying olefin, but you guys are used for alkene. Is the alkene going to be is it going to be Z or E in this case? So Ali says Z. Does anyone else agree? Or do we get E? So if we look at the original Wittig, right, this reagent here, right, is this stabilized or unstabilized? And by stabilization, I mean, I'm really just referring to the carbanion part. Is there anything that's stabilizing that carbanion? Just forget about the triphenylphosphine part. What's stabilizing the carbanion? No, I said forget about that part, right? That the PPH3, right? We're not really we're the R groups attached to it. Well, no, there's no pH on there yet, right? It's technically just an ethyl, right? So that's why Ali here is correct. It's going to be Z, right? Is what is meant by stabilization on a Wittig, right? Is anytime you have this, Wittig reagent, right, and this carbanion, the groups here, right? If R is something like, I guess, R equals H, or really like any alkyl groups, right? That's going to be unstabilized because you technically have a carbanion there, right? The way you stabilized a carbanion, is it going to be electron withdrawing groups or electron donating groups? withdrawing, right? It's negative, right? So we want something that could pull away the electron density, make it less reactive, right? So whenever you have like kind of carbonyls next to it and stuff, then you will have what's called a stabilized Wittig. So in this case, we are using an unstabilized Wittig. So your final major product, right, is going to look like, what's it? EPH, oops. And technically it's just H's on the other side, but it's going to be Z to each other. Here, I'll just draw the H's for clarity, right? But the main thing is those two big groups, right? They are on the same side, right? That comes down to like really the electronics of the reaction, if I remember correctly. When you look at the Newman structures, right? You'll basically see like when it's trying to form the Z bond, right? I think it's like the phosphorus or oxygen that help electronically stabilize that transition state. But
Sharu,
yeah.
so the R for in this scenario, it's the methyl, right?
Yeah, it's technically that methyl group, right? So that is an alkyl group. So actually, let me finish writing what I wrote here. This is unstabilized, and then R equals some sort of electron withdrawing group, right? That's a stabilized Wittig, right? So with the unstabilized Wittigs, right, it's going to be stereoselective to the to the Z isomer, right? With stabilized, it's going to be E, right? And this is that's why this reaction is really one of the most powerful reactions. And I don't know if they won a Nobel Prize for it, but it's stereoselective depending on the conditions, right? And it's actually stereodivergent if you change one of the reagents, right? Basically, if you change the type of Wittig, right, you can go for a Z product or you could go for an E product, right? And those kind of reactions are always really important in terms of, synthesis, because you get that ability to choose, right? So yeah, let's just do examples of that. Yeah, well, unfortunately for you, they just awarded the Nobel Prize to organic people this year. Nate McMillan at Princeton. So anyone know what the driving force for this reaction even is? Why this is irreversible? What we didn't really draw here was technically, I guess, what is it? Oxygen like that. I guess we could draw it the other way, would be better. I don't know if he kind of mentioned this, right? But really, the reason why this reaction goes forward, right, is just gonna draw it down here, right? So this is the other product that formed, right? This is like I guess triphenylphosphine oxide, whatever you want to call it. But oxygen phosphorus, the oxygen phosphorus double bond is one of the strongest bonds in organic chemistry, right? So being able to form that bond is really what's like kind of the driving force of this reaction, right? PO bond, very good, right? So that's why this reaction goes forward, and it's not reversible. It's because when you form that oxygen phosphorus bond, it's not going to be able to go backwards because you need a lot of energy in order to break that double bond, right? And it's a really, really good bond to form, right? And as you see in that kind of second structure we have here, right? That's what's happening there, right? And that's really what the driving force is. Okay, so yeah, we have kind of good overview there of the Wittig. Let's do some examples of it.
Can you go up like for 1 minute or less? No, the one above. Yes, thank you. Here, thanks.
Okay, let's find some. Not really that many questions. It's fine. Okay, let me paste this question. And then we'll move on to carboxylic acid stuff. Okay. Actually, I'll let you guys take a minute or two to try it based off, and I'll leave what we have up there. In terms of the thing there, right, is draw out the major products for both A and B over there.
The B is also Wittig reaction.
Yep. All right, this is technically the modification. What is it? HWE, I think that's what it's called. Got the full name of it. Something Wadsworth's Emmett, I forgot. But it's still a Wittig type reaction. It's just slightly modified.
Is there like
Okay.
a list of all like Wittig reagents like that we can recognize?
I mean, it's not really about a list. It's really if you understand what kind of groups are next to the carbanion, right? I mean, I'm sure there are a list of them, right? You could probably find one online. I don't know if the textbook has one, right? But if you understand what the groups next to kind of that carbanion are, whether they're electron withdrawing or like alkyl weak electron donating groups, you'll kind of understand which way the reaction goes, right? So that's really all you have to look at. So I generally, I've said this multiple times, I don't like memorization in terms of trying to remember stuff like a list or something like that. If you kind of just look at the structure and kind of see, where electron density is, or, what other kind of stabilizing factors are in it, you could always kind of figure it out, right? So here, really the only difference between the, what is it, Wittig, like classic Wittig reagent and your HWE reagent is that you have, it's called that ester here. So it's like a phosphorus ester. Here you have triphenylphosphine. Here you just have this group here, right? Which is a PO group, but essentially it's the same thing, right? It's just somebody later on, decade or so later, maybe a few years later, realized, oh, we could use these type of reagents as well for a similar reactivity, right? That's all it is. But the reaction occurs the same way, right? In terms of, the phosphoryne, or whatever you want to call it, right? That's always going to be dependent on the R groups attached. And yeah, Chemraj, the carbonyl, yeah, it basically gets essentially you're like when you have something like this, right? It is becoming an alkene, right? And this R group, whatever these are, this R is what's attached to the Wittig, right? So if your Wittig is something like, let's say, I don't know, PH3, right? A good way I always look out in terms of how to get the product of this, right, is if I cut this in half, right, and whatever the rest of this is what's attached to where it basically replaces that oxygen. So here I have technically, what is it, CH2, right? So the product, right, whatever the rest of these R groups might be, the product would be now an alkene, R groups here, right? And then in this case, it's just CH2, so you could just leave it like that. Right, so if I had, oops, this just got stuck. Oh shoot. Everybody still see the screen? There we go. All right. So if we had something like, I don't know, right, like that, then all you're really attaching here, right, is this to where the oxygen is. So if you want to draw out the alkene now, right, or really, if you think about it, you could replace that the PPH3 with the R groups, right? Whichever way you want to look at it. So now it'll be, what is this? one carbon, 1, 2, 3 carbons, right? So 1, 2, 3. So I'll just keep track of your carbons, right? But yeah, that's a quick way to kind of get the products for the Wittig, right? Is literally just see what you're replacing. Like the double bond is the same in both the carbonyl and the Wittig, right? And then you're just replacing one part of it. Okay, so for this, let's go for the first one, right? We have a Wittig reagent here. Is it stabilized or unstabilized?
Can you just go to the right side for a couple of seconds? I want to take a picture of that real quick. And thanks. You can go
Yeah, you
back.
guys know like these notes are available, right? So I don't know. I mean, I mean, if the pictures help you guys, I've noticed some people, you know, they like take pictures during the thing, but like the notes are directly available where you get to see.
True.
Yeah.
Are you posting this recording right after the session, or do you usually wait a while before posting?
I mean, whenever it's done converting, I usually post it within the few hours. Unless I leave, then I usually post it late at night. It's usually up within the next few, by the next day at the latest. I mean, just check the OneDrive; it'll be up there. Anyways, so this is unstabilized, as we said. What are you asking for there, Mohammed? The notes? Yeah, it's in. I just put a link tree in the WhatsApp group description, so that has the links to the recitation recordings, the notes, and your Zoom links as well. Okay, so this is unstabilized, right? So in terms of products, right, what we could do here, right, is right, you could literally just replace the PPH3 with the R groups, right? So what R groups we have here? We have this, right? We have this. And that's how our product is going to look. Getting the products is actually not too bad if you kind of know what you're doing. The mechanism is the most confusing part of this reaction, but getting a product is not too bad. But is there any stereochemistry here? Did I draw this correctly? Incorrectly? Yep. So as Eric said there, E and Z is not actually, doesn't make a difference here, right? Because here we have the same we have a symmetrical carbonyl, right? So you have no kind of stereochemistry because, right, if you tried to do the stereochemistry to this, right, you always cut the alkene in half that way, right? You look at each R groups. Technically, this would be priority 1, but on the other side, they're both ethyl groups, so you can't really prioritize one over the other, right? Yeah. No stereochemistry. Just write that. Let me get the product for the second one, and then I'll show you the mechanism for the first one. Okay, so this one, same thing, right? We could kind of think of this is where our like your P and your carbanion is, right? Oops, it's the same color, right? So this was our double bond, right? And then essentially we could kind of cleave off this part, right? Then we have 2 R groups here, right? And in this case, is this stabilized or unstabilized? Stabilized, right? I mean, it's slightly modified, but you could kind of think about the HWE reagents as a stabilized, right?
Why did you
Right.
cross off the left side?
Just so it's easy to draw the product. Like this is kind of just a tip in how to get the product, right? So if we cross that off, right, we could just draw the other R groups, right? That's all I'm doing here, like I did in the first one, right? I could have done this too, right? To get your product. So anyways, will the basically, so you have CH3 and H here. CH3 is a larger group, right? So in terms of relation to this kind of ester here, will it be on the same side or opposite side? It's going to be E, right? So it's going to be opposite, right? So our CH3 will be here. That'll be your methyl, Me, that'll be your H. So your final product, right, is going to look like, draw this on the top here, draw this, and then we said it's going to be E. It's going to be, or you could have honestly drawn it the other way too. It doesn't matter. Yeah, this should be an E alkene, right? That's what I was saying. Getting the products for these kind of Wittig or HWE reactions is not too bad. It's really just kind of seeing what groups connects to what. So the way I always like doing it, right, is draw that double bond between the phosphorus and the carbon, right? And then you could kind of replace the phosphorus part of this entire thing with the R groups off your carbonyl, right? Or you could have, replaced the oxygen too, whichever one's easier for you, right? But I think it's pretty simple for getting the products. In terms of the mechanism, yeah, Mohammer's right there that it's basically the same one as before, but I guess, for the sake of doing it. I mean, do you still want to see it? I mean, because it's literally going to be the same exact thing as what we have here, right? All that's going to be different here is that, what group did we have here? We had a propyl group instead, right? I guess I can just do it again one more time. It's not an issue.
The lone pairs became double bonds. The carbanion, did they become a double bond on the reagent?
What do you mean? I just showed it like that just to show you what the product is. I don't remember the exact mechanism for the HWE. I think it's a slightly different than the Wittig. It's
Do you mind like wiping off the purple on the reagent on the right side?
It doesn't really make a difference, right? It's just purely to show you how to get a product off your reagent, right? It's just for the ease of drawing your product, right? It's not about removing something or like actually, it's literally just kind of think of that as an overlay, right?
Oh no, I didn't get a chance to write it in my notebook. That's why I just wanted to look at my notes. Thanks.
Yeah. This is in your textbook, by the way, but let me just X that out here without removing the structure, right? So same thing over here, right? Just kind of X that out there. And that I'm literally just overlay. So if anyone is still confused, what I was doing to get the products was just overlaying kind of my alkene over this, right? That's how you can quickly do it on your exams, right? Is if you overlay it, right, then you know what groups are attaching to the carbon, right? So let me just redo that mechanism for, I guess this would be 19.34. Yeah, what's up?
Instead of doing the mechanism, could you just like show the old one? Because I didn't catch it. You went really fast on it. The one you have, right?
I'm just gonna do this again. It's gonna be literally the same thing.
Okay.
And you could always go back in the recording to watch it, because we kind of spent more time than I was hoping for on the Wittig and stuff here. But I mean, I figured it'd be confusing to people. It's the most confusing out of all of them. Okay, so we have this. What else do we have here? We're gonna use our PPH3. I'm gonna draw it slightly differently. I'm gonna draw the yielded form, right? We have PPH3, and then we have what? 1, 2, 3 carbons attached. So 1, 1, 2, 3, right? So this is plus, this is negative, right? So now what happens is, first thing that happens is basically a 2-2 cycloaddition, right? This oxygen, this, what is it? This bond between the oxygen and the carbon, right? The electrons, you could kind of think of them as just going to here and then attacking the phosphorus, right? Or we could just draw one arrow, right? Showing this oxygen phosphorus bond forming, right? So that's the first arrow, right? As your oxygen phosphorus bond is forming. And then at the same time, what happens is a carbon-carbon bond is forming between the carbanion here, right? And the carbonyl carbon, right? So that top one, the top arrow, right, is going to be the oxygen phosphorus that forms. Let me actually use different colors so I could show you in the next product. right? So now if I draw it here, right, this is oxygen, this is phosphorus, carbon, right? And then the red arrow is this bond, the blue arrow is this bond, right? And then what's connected to these, PPH3. Here we have, what is it? This is the carbon, so it's 1, 2 coming off, right? And here we had 2 ethyl groups, right? Like that. Yes, it is a concerted mechanism, right? It's what people claim that it's most likely through. Like, once again, these are all proposed mechanisms, but it's what people say is that it went through kind of a cycloaddition, right? So it's technically like one of those pericyclic addition reactions, right? But the kind of what's cool about this is that it's not like normal cycloadditions. It is slightly ionic in nature because of I mean, it depends on how you think about it, right? If you think about it in the Yelid form, it'll be ionic in nature because there's a plus and minus charge. But if you think about this as a double bond form, right, then technically it's more classic cycloaddition, right? So different people say different stuff. But anyways, this is now, right, these are the bonds that we form. The red arrow is that oxygen phosphorus bond. The blue arrow or the blue line is the carbon-carbon bond. Now, the next step that just happens is you basically have this oxygen phosphorus double bond forming, right? So that completely removes, now let's use another set of colors, right? So this is going to break this oxygen carbon bond, and now you form a carbon-carbon double bond with, we'll use pink here, right? So you're breaking a phosphorus carbon bond, and you're breaking an oxygen carbon bond. And what this forms is the oxygen phosphorus double bond. And that really, it's that orange arrow here, that's the driving force of this reaction, right? Is that that bond you form now is one of the side products, right? It's a really, really strong bond, right? And going forward, it's really favored to form it, but going backward, it takes a lot of energy to break it, right? So now your final product, right, in terms of all these colors I'm using now, let's draw the final product. It's going to be, that's it. So we had a pink and we had a blue, right? So that's the double bond, right? What's connected here on one end, right, is the 2 ethyl groups. And what's connected here on the other end is the other kind of ethyl group, I guess, right? Right. And the other thing we formed here was pH3, phosphorus oxide there, right? And that's how you get your final product. Hopefully the colors make this a little bit simpler to understand, right? Okay, let me just see if there's any more practice questions. Probably at the end of the chapter, maybe. Yeah, I just want to do maybe one more Wittig question, just for practice, and then we're gonna end the chapter 19 here. There is not really that many Wittig questions. It's weird. Well, the one before was the same thing, right? Let me zoom out, right? It's still the same thing I did, right? So what Mohammed was saying there, all I was changing is the groups, right? Here we had a methyl group on the triphenylphosphine, right? Then was an ethyl group there, and now instead of the pH and H here, it's 2 ethyl groups, right? Mechanism never changes, right? It's just really what groups are attached, right? And that determines stereochemistry, right? In this case, in this specific example, there's no stereochemistry, right? Because the groups are the same, right? But let's say if I slightly changed all of this, where I had, what is it? Say I had H here, and then this ethyl group, right? Then your final product, right, is going to look like your ethyl from the top, right? And then you have your H and you have your ethyl there. And this would be Z, right? And that's because this is unstabilized. This was stabilized, right? And then it would be E, right? So maybe I'll give an example of that too, right? So if we had something like PH3, I guess this will serve as the other examples since the textbook doesn't have many. Right, so if we did this with that, right, now our final product will be our H, right? This would be. That's really the outcomes of the Wittig. It has to do with like, and some people say it's because of steric interactions, but if I recall correctly, it's because of electronic stuff. I mean, we're gonna take our break here, so let me actually, I have some slides on this. So we're gonna take like a 5-minute break before we start chapter, I guess. Was it the next one is 20 or 21? I forget. 20. Yeah. Well, actually, let me stop the recording. Then I could have this in 2 separate recordings.